We're going to just evaluate a few composite functions and introduce the kind of notion behind it. So when we talk about composite functions, let's go ahead and start with this. The root here, you kind of hear the word compose, which means to put together. But when we talk about composite functions, let's say we have a couple of functions, f of x and g of x. And really what's happening here, recall, is this. What I'm doing is I'm saying I have some x values, and I'm plugging them into f of x. Okay, and what happens is, under this rule f, this is the rule, I get some output y, okay, and we call these output values f of x values. But the interesting thing is, what if I were to take these now? These is just some set of numbers here, some y values that we have. What if I were to plug them into the rule g of x, which is an interesting thing to kind of say. So, before we'd say g has its own rule, and what I get here is I get g of whatever I'm plugging into it. But what I'm saying is, what if I took the y values here, all of these y values, and plugged them into the rule g? I would get some new function that we would refer to as this, okay? And we would read it as, we say g of f of x. And this is really just kind of a fancy way of saying what we'll do is we'll take the outputs of one function and make it the inputs of the other function. So I want us to know this. We could say we could find f of g of x, or we could find g of f of x, or we could find f of x, or we could find g of x, or we could really compose these any way we want to. But really what's happening here is we're saying this. For instance, on this f of g of x, we're saying let's take the y values for this function and let's plug them into this function f and see what we get here. So in terms of evaluating this, what I'm going to do is I'm going to work through a couple of examples here that show you how it is that we find composite functions. But I'm going to start with this. It says, we'll substitute other functions into these functions. So what I want to do is I want to find all of these, given that f of x is some 2x plus 1 and g of x is some 3x here. So I'm going to rewrite these so we can see them a little bit more clearly here. We say this is some function 2x plus 1, and g of x is equal to 3x here. So let's keep this in mind. This first example, I just want to find f of 3, which, recall, when you say f of 3, what you're really saying is this. I have some rule, and the rule is 2x plus 1, but what really was happening here is this. We're saying whatever we're plugging into the function, which in this case is 3, wherever I saw an x formerly, what I'm going to put is a 3. And so we get this here. We get 2 times 3, of course, is 6 plus 1 is equal to 7. So we get this output here. And we say that this is equal to f of 3. That's what this is. It's the y value when x equals 3. What I want to do this time is this. I want to find f of g of x. Now, the interesting thing here is this. I'm going to rewrite this. What we're saying is this. We are plugging the rule g of x into f of x. So just like formerly, we said what we'll do is we'll take this x value out. Wherever I see an x, we'll take it out, and we'll put in, previously we said 3. This time what we're going to do is we have this for an input. Okay, so we say our input here is g of x. Now, g of x, we know what g of x equals. G of x, its rule is 3x. So what we're going to do is we're going to do a substitution here. And we say f of g of x. That's what this really is. We say f of x, when we plug g of x into it, we get this new function where we get 2 times, in parentheses, we say this 3x is what it equals here. So when we simplify this, we really get 2 times 3x is 6x plus 1. What we're saying is f of g of x is this new function, and its rule is this. So we say f of g of x. When we plug all the y values of g of x into the f function, we say we get 6x plus 1. Okay, so we're going to try this again here. This time, I'd like to find g of f of x. And my question is g of f of x going to be the same thing as f of g of x? So we're plugging f of x into g of x. Let's talk about g of x's rule now. G of x said 3 times the input. So we're going to write 3 times blank, and we're going to put in our input. And our input this time is f of x. Wherever I see an x, I'm going to put f of x. So I'm going to say, well, 3 times f of x would really be 3 times 2x plus 1, which when we simplify this, we could just go ahead and distribute here. We get 6x plus 3. So this thing right here, I'm going to give this a name. We're going to call this g of f of x. This is what we get when we plug all the y values for f into g. We get 6x plus 3. Now the question was this the same thing as what we got down here for f of g of x? And we got 6x plus 1 before. So one bold kind of exception or statement we want to make here is this. G of f of x equals f of g of x sometimes. So here's the deal. This may sometimes happen, but it is very not common. Okay, so there are certain instances where it will happen. So I want to look at one last example. We're going to find f of, and I'm going to say f of x here. Could we compose a function with itself? Could I plug a function into its own rule? And yes, you can. We say plugging into this rule, we say 2 times my input plus 1. This was formerly an x. Now we're plugging in f of x wherever I saw and x. So this really becomes 2 times our rule for f of x plus 1, where our rule for f of x, recall, is 2x plus 1. So wherever I see an f of x, now I'm going to substitute 2x plus 1. And go ahead and simplify this. We get 4x plus 2 plus 1. And when we combine like terms here, we really end up with 4x plus 3. So we'd say f of x is this new function, 4x plus 3. And so that's how we'll compose functions. It's just a double substitution.